Hey there, buddy. Let's do some practice together drawing some ray diagrams for lenses. We're going to kind of do this very similar to how we did it for mirrors, although I probably won't do as many examples with lenses as I did for mirrors, because hopefully we start to see some patterns and recognize some things right away. So you're going to want some lenses, if you got them. You're going to want some different colored markers or pens. Definitely going to want a ruler. You're going to want all these handouts that I printed off for you. So you're going to want the diagrams that look like that, and then your calculator. So let's get rocking and rolling. Let's put those aside for just a second. So kind of like we did with mirrors, I've drawn these things relatively to scale, and I've already got the foci plotted for you on here, because you can't just measure it the same way we did with mirrors. That's one difference. Over here I've kind of got some directions and guidance for you guys, and then a table at the bottom of each page to summarize what you got so far. So let's look at this first example of a converging lens together. First thing we're going to do is measure the focus, measure the focal length. And so we're going to grab our ruler and we're going to measure from the center, there's a dot in the center of the lens, to the focus that's already plotted for you. And again, the copy, scan, print process has changed my dimension, so we're going to use exactly what it says. So I measure that to be 3.2 centimeters. So this distance right here, that's F, that's equal 3.2 centimeters. Now that's the same as this distance right here. So because a lens is reversible, like I can hold it like this and then I flip it over and I get the same thing, it has a focus on both sides. Light coming from this side, parallel rays would be focused there. Light coming from this side, parallel rays would be focused right there. And so that's why there's two foci that we can use to figure out what's going on with our image. The first thing we're going to do here is draw a 1 centimeter tall arrow at a point to the left of the lens, so we're going to stick to this side, exactly halfway between the focus and the lens, so that the object distance is 1/2 F. That's going to be 1.6 centimeters to the left of our focus. So we're just going to grab our ruler. 1.6 centimeters to the left is going to be like right there. And then we're going to draw a 1 centimeter tall arrow at that point. Just like that. And we're going to label that our object. So that's the thing that we are looking at through the lens. And then we're going to plot two rays to locate and then characterize and describe the image created. And so, move that out of the way here. Our first ray is still going to be the ray that starts off parallel to the principal axis. So make your ruler as parallel as you can to that axis. Goes to the center. And so by center, I mean a line vertical like that goes through the center of the lens. And so like that's what I mean by center. Draw it to that line. And then that ray again refracts to the focus. Now, because there's two foci, we have to kind of keep this straight. The ray that's parallel over here refracts to the focus over here. So parallel, and then line it up. I did not do a very good job of lining it up in that case. Okay, so there's ray number 1. The second ray that we can draw is still the one that goes straight through the center. For lenses, that's kind of easy because the center is right there at the center of the lens. And so we just line the top of that object arrow up with the center. And then that ray goes through the center just like that. And if you look carefully at those, you want to label that number 2, you can. If you look carefully at those rays, you'll notice they never cross. They're diverging. And so that means we need to trace them backwards. And so let's line our ruler back up with that. And let's use a dash line to extend them backwards behind the object. And it's a good practice, especially with the first one, just to extend it back as far as you can. You never can really tell how far you need to extend it backwards just by looking at it. When we do the second one, remember that we trace back the ray that enters our eyeball, which is this ray over here, not this parallel bit right here. So this is what your eyeball thinks the light is doing. It thinks it's coming that way so that it came from like back over there. So line your ruler up with that and then trace that backwards. And again, make sure you use a dashed line when you trace rays backwards because it's not an actual ray of light. More like that. Okay. So once we've done that, we should be able to see that those cross right about there. And so that's where our image is going to be located. Let's draw our image arrow right there. And let's label that image. Okay, so the next thing we're going to do is figure out how far away that is, measuring again from the center of the lens. So let's measure the object, should be the image distance here. So line that up careful. Let's use the correct side of our ruler. So I get that to be 3.2 centimeters. So it's kind of like almost right on top of the focus. So SI, sorry, 3.2 centimeters. And then let's measure the image height as well. So my image height is about 1.8 centimeters. So this HI equals 1.8 centimeters. And then since that is a upward arrow, it's pointing upwards, the image height is positive, it's upright. We should probably characterize it as upright, so let's jot down it is upright. Since the image is on the wrong side of the lens, so to speak, like the rays of light are going over here, this is where we should see the image, that means we need to remember to make our image distance negative. And so when you write that down, make sure you write down a negative image distance. So on the other page of the handout, we got a little table here that we can kind of fill in to keep things straight. And so we got a virtual image. Since the rays of light do not actually cross, that is virtual. It was upright. V's and U's look alike. Virtual upright. Our measured SI, negative 3.2 centimeters. You write down what you actually measured it to be, of course. And my measured height, positive 1.8 centimeters. Okay. Over here, I've got some space to actually do the calculations. So let's go through those real quick. Just like for a mirror, I can use the relationship 1 over f equals 1 over SO plus 1 over SI to calculate the image distance. So solving for 1 over SI, that would be 1 over f minus, so subtract that, 1 over SO from both sides. And I'm just going to leave it like that. So I'm going to solve first for 1 over SI equals. So in this case, my focus was 3.2. And then our object distance, where we actually plotted the object, was 1.6. And so you can actually get a common denominator for those. You can say that that is equal to 1 over 3.2 minus 2 over 3.2. 3.2 would be a common denominator between those two. That's why we did like a nice half interval. So no matter what we got for the focus, like half the focus we can get a common denominator for. So 1 minus 2 is minus 1 over 3.2, just like that. And so inverting that, let's not invert it just yet. So negative 1 over 3.2. So SI is equal to negative 3.2 centimeters. So negative again, because it is a virtual image, just like we noted down there. So mine wasn't too far off. Write that down there in the table. Okay, to get the image height, we can again use the relationship HI over HO equals negative SI over SO. And so solving for HI, just multiply both sides by HO. So HI would be, our object height was 1, so 1 centimeter. Don't forget about that negative sign. Somewhere, somehow, don't forget about the negative sign that you get in there. So SI was negative 3.2. Our object distance was 1.6. And so 3.2 over 1.6 would just be 2, 1/2 of each other. Negative times the negative would give me a positive, so our image height should be positive 2 centimeters. Just jot that down here in the table. And so mine was just a touch off, probably because I didn't line up my ray that went through the focus very well. And so 1.8 to close enough for government work. Okay, so that should jive with what we saw when we drew the ray diagram. So I can kind of show you this image. It's kind of difficult to show you images formed by mirrors with the cell phone camera. Lenses, it's a little bit easier. And so here's my converging lens. And if you kind of look at that, you'll notice it's a little bit thicker in the center, kind of like what I drew. And so let's just hold it over something like, maybe that right there. So what you'll notice when I get it kind of focused is that you get an image that is bigger than the original. So like that versus that. And it's virtual. Like you can only see it when you look through the lens. And so if I kind of turn this lens, if you actually look on the paper behind it, you don't really see anything but blurriness. You see a reflection of the lights overhead, but you can't really see an image on a piece of paper there. So this one's a virtual image. You gotta look through the lens in order to actually see it. And it's upright, like it's not flipped upside down when I do that. Points the same direction each time. So what I'm showing you here with this lens matches this ray diagram. So the next one we're going to do, and have you guys try this on your own, is basically the same lens, same drawing. This time we're going to move the object so that it is 3/2 f. So if that is 3.2, 3/2 of 3.2 would be 4.8. And so we're going to put our object 4.8 centimeters from the center of the lens. And again, that should be over here to the left. So instead of being between the focus and the lens, this one's going to be to the left of the focus. So hit the pause button here when Simon says go. Do situation number 2 all by yourselves, and then press play, and we'll do it together. Okay, so let's check out what you did with situation number 2. So in this one, we're going to go 4.8 centimeters from the lens. So that's going to be like over here. And again, we're going to draw that 1 centimeter tall. Okay, so there's our object. And we're going to draw 2 rays to locate and describe the image form. And so the first one we can do is just starting parallel to the principal axis to the center of the lens, and then that refracts through the focus just like that. Call that ray number 1 if you like. Ray number 2 starts at the top, and it's just going to go through the center, kind of like that. And what you'll notice, if you drew those carefully, is that they should cross over here. So that's where our image is located. So I'm going to draw the image. Just like that. And we can go ahead and kind of characterize that thing. You should notice that the rays cross below the principal axis. That arrow points down. So that is an inverted image. And since the rays of light actually cross at that point, we can say that that is a real image. And so you could actually see that on a screen. So if you had a screen right there, you would actually see an image just like you would from like a projector or something like that. And so when we get to the Thin Lens lab, I'll actually carefully video for you guys some real images. I can kind of sort of try to show you one real quick using just the fluorescent lights on the ceiling. Let's see if I can make that work here. So you might get in. You can kind of see an image of like the light bulbs on the piece of paper there. Not going to work very well. So it's not really working too terribly well for me here. You can kind of sort of see, like right here, you can see the outline of the light bulbs and the overhead lights. There's two of them that are on. And you kind of sort of see in focus that there's a line between them. But it's probably not showing up very good on the camera. So hopefully I can video for you when the room is dark, an actual real image on a screen, and prove to you that you can actually see those kind of things on a screen. That's kind of the limitation here of doing this kind of stuff virtually via video. Okay, so go ahead and measure those things and then do the calculations and make sure that your calculations and your measurements are somewhat in agreement with each other, and then you'll know that you've done the calculations correctly. We're going to move on to diverging lenses. Diverging lenses are typically thinner in the middle than they are on the edges. Let's get this bad boy right here going. And we kind of need to remember some of the rules for diverging lenses that are kind of similar to the rules for convex mirrors. And we'll go through those as we kind of go. So let's first start off by measuring our focus. Same thing, line up our ruler. This one is 3.2 as well. So this distance here, F equals 3.2 centimeters. But we gotta be careful. For a diverging lens, just like a convex mirror, we have to remember to make the focus negative. Nobody's going to remind us of that. We've got to remember that a diverging lens, the focal length is negative when we use it in our calculations. We're going to put a upward arrow, again half F, so 1.6 centimeters to the left here. So let's measure that real quick. I'm not going to draw the other focal distance there just to save some space. So 1.6 would be like right there. We're going to make a 1 centimeter tall arrow. And then on this one, you really want to make sure you label things carefully. So that's our object right there. Okay, we're going to start off drawing our rays the same way. We're going to start off with a ray that is parallel to the principal axis. So top to the center of the lens. Now a diverging lens doesn't cause this ray to be refracted to this focus. It causes it to be like refracted that direction away as if it came from this focus. So once your ray meets the center of the lens, now we turn our ruler such that it lines up with the focus behind the lens like this, and it goes up and away, like up and to the right. And then in order to show that it came from the focus, we can go ahead and do a dashed line to indicate that. This ray right here refracts away from the principal axis as if it came from the focus right there. And so let's do that. and that is ray number 1. Ray number 2 is still the same. Ray number 2 for lenses is easy. We simply line our ruler up with the center, and there we go. There's ray number 2. So just like before, notice that those rays are diverging from each other. They're not going to cross, and so we need to extend them backwards. Well, they're already extended backwards. Ray number 1 we've already extended, so this point right here is the point where our rays are crossing. And so here is our image. That's why it's important to label things carefully on this one. And so let's kind of zoom in just a little bit here. The object and the image are like almost right next to each other. Notice that the image is a little bit smaller than the object, but it's still very close to the object. So looking through a diverging lens, we're not really going to change what we see a whole lot. I'll show you guys that here in just a second. We can characterize that thing that is a virtual image, since the actual rays of light do not cross, and the arrow points up, so it is an upright image as well. So let me grab my diverging lens real quick here. There it is. So here's my diverging lens, and so when I hold it, like right there, like you'll notice that the image doesn't change a whole lot. It's just a little bit smaller than it was before. If I kind of hold it like halfway there, you'll notice you can see more in the lens than you can without it. Like if you just kind of imagine a circle right here, like that circle kind of would include just a little bit of that lens, but not all of it. But when you look through the lens, you can basically see all the lens that I drew on the piece of paper. So one of the useful things about a diverging lens is it lets you see more stuff than you would without the lens. And so if we kind of like go, all right, you know, what's in that little circle right there? You know, okay, we don't see a whole lot. Now with that in the place, camera will focus, you can see more stuff. And so if you have a camera that's got a fisheye lens, that's what this is. You know, it's a diverging lens. And so you can use these things to see a wider view than you can with a converging lens. And so if we bring the converging lens back in, converging lens took a little bit of stuff and made it larger. Diverging lens lets us see more stuff. And so if I want like a nice cool panoramic shot, like when I'm snowboarding using my GoPro, we'll use a lens like this. And then you can put them together to get like compound effects and things like that. So hey, I can see a lot of stuff there, but it's all in focus. The other cool thing about diverging lenses is that everything's always in focus. Like you can get a lot of stuff in focus with a diverging lens, whereas with a converging lens, you can't really get a whole lot of stuff in focus. That's going to be clear when you do the next example. Zoom that back out. So speaking of the next example, actually let's do the calculations together real quick for that one. So go ahead and measure your distances there. And then we can calculate the image distance again by doing 1 over f minus 1 over SO. So 1 over SI equals 1 over, and it's important here, like you have to remember to make that focus negative for a diverging lens. Like that's a key thing you got to remember here. Minus 1 over 1.6. And so when you kind of, you know, reduce that and get a common denominator, don't forget to move that negative sign up there, otherwise you'll do the wrong operation here. And so that would again be 2 over 3.2. And so minus 1 minus 2 would be minus 3 over 3.2. And so SI would be negative 3.2 over 3, which is going to be like just a touch over 1. So 3.2 divided by 3 is like 1.1. And don't forget the negative sign in there. So if I took my ruler and measured from the center to my image, I should get about 1.1. Let's check that real quick. just a skosh under, like 1.05 or so. These are kind of difficult to draw because there's not a whole lot of space in there. It's kind of tight. The negative sign, again, tells us that we got a virtual image. So without doing the ray diagram, I can know that I got a virtual image because I got a negative image distance. And there goes the lights in my classroom, of course. So I'm going to leave it up to you guys to do the second example and do all the calculations and everything in there. As you're working today, if you have questions, need clarification on something, please just let me know and we can work on more things together. Till next time, ta-ta.